Okay, so here's the class video then for section 4.1. So let's start with an example. So let's talk about finding the local max and min for the following problems. How many people know what a cube, everyone realizes this is a cube root? Because it's to the 1/3. What does a cube root look like? Anybody remember what the graph looks like? This is the, yeah, so let's see. So we've got cube, the cube looks like that. So the cube root looks like that. Well, not quite so, it doesn't do like that. It's not an asymptote. So this is what a cube root looks like. What does this on the inside do? This is a reflection and a shift. You always reflect first, then shift. So this thing is going to look something like that. Something like that. So at this point that was here is now coming through at 1. Something like that. You don't need to know that. I just wanted you to kind of see where we're going. So, so if I want to find local max and min, looking at this, do I expect to find one? There's no, it doesn't go up and come down. It just is always decreasing. So I don't actually expect to find one. So sometimes if you kind of know what you're looking, if you have an idea in your head what you're looking for, it can, again, help you verify that your answer makes sense. So the first thing we'll do is do a derivative. Is this a basic? No, because it's not just x to the something. So this is some quantity to the 1/3. So this is a what situation? I need to use a chain rule. It's a composite function. So the first thing I deal with is the outside function. So we have 1/3 comes down in front. The middle stays the same. And what do I get for the exponent? Negative 2/3, right? 1/3 minus 1. So this stays in here. And now, am I done? No, because I haven't taken care of the squiggle. So the derivative is times negative 1. Okay, let's clean that up. So minus a third times 1 minus x to the negative 2/3. Next time we're going to start doing second derivatives, where we're going to start with the first derivative and just do the derivative again. That's the form you want for that, right? Because it's already in power rule form. But when it comes to substituting, I find the negative exponent to be a little confusing myself. So I'm going to rewrite this way. I'm just putting the to the 2/3 in the denominator. Okay, so now I need to think about my sign chart. Where's the numerator equal to 0? Nowhere, so I don't get anything from that. Where is the denominator equal to 0?
It's not negative.
Yes, thank you. That's going to be really important. Yes. Where is the denominator equal to 0?
1.
1. Does everyone see it? Right? 1. All right, so 1. Is that a point on the graph? It is a point on the graph up here. So I'm just going to kind of leave it like that. If it were an asymptote from the beginning, I would dot it in as an asymptote just to reinforce that. But this is actually a point on the curve. That's okay. All right, so now let's start plugging in. 0, I could plug in 0 and 2. Or, what does to the 2/3 mean? I take this value, I square it, and then take the cube root of it. Anytime you square something, what is it? It's always positive, right? So this denominator will always be positive. You can plug in some points and find out. If you plug in 0, you'll get 1 to the anything we remember as 1. So we get a negative 1/3. These both turn out to be negative, which makes sense with what we were expecting. All good. So this is going like this and going like this. And in the middle, is it going through a 0? No, in the middle here, because the 0 is in the denominator, it's infinite. So this really comes in a little bit tighter, more like that. It ends up being infinite, infinite slope at that point. So is there a max or a min? Down, down, no max or min. So no max or min. How do we write increasing, decreasing? Increasing? None. Decreasing? Is it decreasing from negative infinity to infinity? Yeah, because this is, yeah. I don't usually write it that way. I usually leave out this one because it's actually, at this point, it's actually decreasing in an infinite way. You could probably write that as negative infinity to infinity. only because at this point it's decreasing, right? The zero's down here in the denominator. If this had been a regular zero, you would break at that point, because at that point this is increasing and decreasing do not include zero. Increasing is strictly positive and decreasing is strictly negative. So this is our set of answers. I'm going to recommend, well, I'll wait till that. When we get to graphing, I'm going to recommend that you kind of keep a list of information off to the side of your page, because that's going to be helpful then to have all the information in one place to start graphing. Here we're a little bit around the board. Yes?
I mean, wouldn't it include zero, but the difference is it's just the behavior, and the behavior is still decreasing at zero because any next point from zero would then be...
No.
It's not instantaneous slope, right? We're talking
It
about
is.
the slope of the graph
This
itself.
is instantaneous slope at this point because the zero is in the denominator. Yeah, instantaneous slope is, and in this case, zero is in the denominator, so it's infinite. I mean, it's vertical at this
So
point.
why do we not include it if we're... I'm confused.
Where do we not include it? Why? Wait. So let me give you a
You said
different...
when you were writing decreasing,
Yeah, so let me give
you weren't writing the
yeah.
zero.
Let me give you a different example. So this one I said it's increasing the whole way. If I had a sign chart that looked like, let's see, if I had this, if I were doing a sign chart for, and I got f of x equals, let's say I got that. That. Where is it 0? At 1. This is always squared, so I'm going to get negative, negative. The difference is this is going to go like this, then flat, and then, sorry, keep decreasing. It is flat at this point because the numerator is 0. So here, if I were going to write decreasing for this one, I would write negative infinity to 0 to 1, sorry, trouble, and 1 to infinity. Because it's not decreasing when it's 0. 0 is not decreasing. 0 is, there's decreasing, flat, and increasing. And flat is something in the middle that isn't in either category. So increasing is strictly positive and decreasing is strictly negative. So at this point, it is 0. So I cannot include that. The other example, it was infinite negative, and so that's a different thing. So the important part, generally speaking, generally, you don't include the points on the sign chart in your increasing and decreasing. You generally don't, because they are usually a place where it's 0. And 0 is not positive and 0 is not negative. All right, let's try another one. Let's try. I don't think I have one of these on the homework. I don't think I have assigned any lens or exponential functions for this, but let's just go over one just to review lens a little bit. All right, so here's another example. F of x equals 8 len x minus x squared. Okay, find local max and min. What do we do? Find the derivative. Okay, so this is a good opportunity to review some derivatives. This is not a product rule. I've just multiplied by a constant. So this is a basic, just 8 times the derivative of ln, which is? Over x. I love that. In unison, very nice. And then the derivative of x squared? 2x. Okay. Now the next thing I need to do is set this equal to 0. Well, let's clean it up first. 8 over x minus 2x. I need to set it equal to 0. But remember, when I'm finding sign chart, I'm looking for where it's equal to 0 and where it's undefined. There's some undefined part here. So anytime you start with even one fraction, you need to convert this to one fraction altogether before you can figure out your partition points. Because we're looking for where it's 0 and where it's undefined. So we need to have one fraction. So how do I combine this into one fraction? Right, so this is like, I'm just looking for common denominator, so times x over x, so I'll get 8 minus 2x squared all over x. Now I can set that equal to 0 or undefined, and I can check the numerator and the denominator. I'm going to go ahead and factor the numerator. I like using factored form anyway, just because I find it easier to plug in for the sign chart into factored form just always. So the first thing I'm going to do, I also like when I'm factoring to have a 1 on my x squared. So I'm going to factor out a negative 2. That leaves me x squared here. And when I divide 8 by negative 2, I get negative 4. All right, well that makes some sense, right? I know how to do that. Let's go ahead and finish factoring. Okay, so what points go on my sign chart?
0, 2, and negative 2.
Yeah. Anywhere the numerator or the denominator is 0. So 0, 2, and negative 2. So remember with sign charts, we're going to do a lot of sign charts. If you're not feeling comfortable with sign charts, just wait. You're going to do about 1,000 of them before the end of the semester. It's going to be really good. All right, so let's put in some test points. Different people have different formats for how they write out a sign chart. It doesn't really matter to me which format you use. I just strongly encourage you to label it, because you're going to have more than one. At some point, you're going to have two. So label it so you know which one's which. And make a big distinction between your test points and your actual points. The points on the number line are really just the x values. So they're just these values that we got here. 0, 2, and negative 2. Nothing else should get a tick mark on the number line. Okay, so negative 3, negative, 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 negative. Did I do that right? Help me out, I'm having a rough morning. I think that's right.
Yes.
Put in negative 1, negative, positive, negative, negative. So it's 3 negatives. Put in positive 1, negative, positive, negative, positive. 2 and 2. And then 3 would be negative, positive, positive, positive.
Yeah, that confuses me.
Yeah.
Which part?
No, I just mean like whenever I do it, I just actually have to like do the number.
Actually find the
Like,
number.
if I try and like
Okay.
memorize negative, negative, positive. I'll
Well, and here's
mess
another
it
thing that
up.
I often do. Here's another thing that I often do. I kind of skipped that this time, so let's do it this other way. So
And
when
then
I
you
put in
find the
negative
y
3,
value
when I
you
put in negative 3, I figure I have 3 factors going across and 1 underneath. So I would go negative, 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 negative. Right? Negative for the first, negative, negative, negative. 4 negatives, positive. So if I put in negative 1, I'll get negative, positive, negative over negative. That's a little bit more, if that helps you, yes.
Is it okay if when we do it, because
You can just compute the number. Yeah, the problem is,
If I
it's-
just do it and then write the number.
yes,
and
that's
then I have the
absolutely
Y
fine.
value,
That's
and then
absolutely
write
fine. The
that.
problem is you're going to find that once you get the hang of this, this is much faster. So if you want to keep doing the numbers, that's totally fine. Just understand you're going to be spending time finding information you don't need. So I just throw that out there for you. So if you can get to where, if you can practice this to where, you're comfortable doing it this way, minus, plus, minus, plus. And again, a lot of times I will actually write out, not this, I should leave that off, but I'll write out kind of a visual, however the factors are, and that helps me keep track rather than trying to keep track in my head. And then here we have, this one's negative. So what does that tell me? That tells me it's going up, down, down. But there's one big thing that we forgot. I even had it on my notes. Remind them about. Let's come back here. Is there anything that we know about either of these functions that might change that sign chart? Look at the original functions. Is there anything we know? X squared, that's just, there's no restriction or anything on that. What do we know about ln x? Anyone remember what ln x looks like? There is no ln of a negative number. It does not exist. The domain for this original function does not include all of this. So really, we should not even have done that part. When you set up this number line, it should set up like this, 0 and 2. And if you want to, knock it off like that if you want to, but we should not have even found signs over here because it doesn't make any sense. It makes sense in the derivative, but back in the original function, you can't put that number, it does not exist. So it's really important actually, and this comes into play when we start looking at business applications. Clearly, we can't have negative prices. We can't have negative number of items. We can't have negative cost. And so we're going to end up lopping off parts fairly frequently. And so it's best to do that up front. So teachable moment from my mistake. So we got to here. So what do I know about max and min? And what do I know about increasing, decreasing?
Give a max and two.
Yeah, this goes up and then down, so I have a max. And here's an important thing. When we come to graphing, so remember, where is a what answer? X. And what is a
Y.
Y answer. When we go for graphing, we're going to want to graph the whole point. We're going to want both. So let's just get in the habit of when you write max, you write a point. So 8 ln 2 minus 4. We're just going to leave it like that. You could get a decimal equivalent for that. That'd be totally fine. So just get in the habit of when you write max and mins, write those. Okay, so increasing just from 0 to 2, and then decreasing from 2 onward. Okay. Is that all right? Okay, so let's look at, there's one more piece I wanted to do on this, and then we're going to get straight on to elasticity, which I didn't put on the minute to win it because you're not going to have to memorize that. I'll give you all those formulas on the test. It's just a fairly easy application. I just wanted you last night to have some practice just actually computing it, and now today talk about what it means. All right, so one more bit about this. Okay, I'm going to give you something to draw. So I'm going to write out a sign chart. So let's say that you were given this sign chart and then this points of information. We're just going to talk about what we know about the graph, just based on the sign chart and the points that we have. So here's our sign chart. This is undefined here, 0 here, and 0 here. So this is describing the derivative. And we have plus here. The book shows it as several pluses going across, plus. It puts a 0 there, indicating that the derivative is 0 there. That's fine if you want to do that. Minus until it gets to another 0, and then plus. I typically, when I do that, I don't have multiple pluses and minuses, so you don't have to either. Normally, when I do a sign chart, I would just have this. That would be my sign chart. So mine's just a little simpler, but that's what you're going to see in the book, just so you know. Okay, and then I also give you this information. I give you a table of values. So here are x values. If I give you x and f of x, what is f of x really? That's the y value, right. So I'm going to give you a whole table of values. So we have -2, 3, -3, -1, 0, 0, 2, 2, -1, and 3, 0. So the question is, what can we tell about the graph from this? So today we're talking about first derivatives. Next class we're talking about second derivatives. And then the class after that we're putting everything together for graphing. So we're just going to touch on graphing a little bit here, not a lot, but just kind of in preparation. So if I'm looking at this, I might first like to just go ahead and plot these points, right? They're points on the graph, so let's just go ahead and plot those. So -2, -3, -1, 0, 1, 0, 0, 2, 2, -1, 3, 0. Did I do that right? Check because all right, so now let's see what we know. This tells me that it's increasing up through -1. Right, so that tells me that I'm increasing through this point to that point. Does that make sense? It's increasing. And then it's increasing again, going up this way, all the way to when I get to x equals 0. And then it starts decreasing, and then it starts increasing again. Does that make sense? Does the graph really look like that? Have you ever seen a graph that's all straight lines like that? No. There's going to be some curvature to that. That's what we're going to pick up next time. So the first derivative, this is all it tells us. It tells us really just up and down. It doesn't tell us whether it's that straight or curved this way or curved this way. The curve comes from the second derivative, so we're going to do that next time. So I just wanted you to get a sense of, I think I gave one problem on this. And really all I'm just looking for is just kind of a dotted up and down, you know, just roughly what's it doing. Okay. All right, so let's look, any other questions on that? All right, let's look at elasticity. So this is actually section 3.1. So we got a little bit of that in there too. I mean 3.7. Yes.
Which of those graphs do we really need to watch out for in terms of cutting off like sides?
In terms of what?
Like cutting off, like you know how you cut off sides like on the sign chart? Which graphs do we need to watch out for? Like
Just anywhere where the domain is not all reals. Is that what you mean?
Yeah.
Yeah, it's a domain issue. So in the case where so most of the functions we're going to be dealing with are going to be polynomials and rationals. So polynomials, what's the domain of any polynomial? All reals. And what's the domain of a rational function? What are the limitations? Rational meaning ratio meaning fraction.
Isn't that the asymptotes?
Right. Denominator can't equal 0. That's going to be where your asymptotes are. Or if any factors cancel, a hole in the graph. So really for us, the only domain issues we're going to run into are business applications where we know certain values can't be negative and asymptotes. Okay, so let's look at elasticity. This is actually kind of a cool elasticity. This is actually kind of a cool thing. So here's a question for you. Chief Financial Officer, CFO, announces a company's revenues have increased by $50 million last year. Are you excited?
I mean,
Depends. I don't know how much
Wait. Depends on what?
how much they're projecting.
How much they were projecting and,
What the money's actually worth?
yeah, and maybe
your cost.
if you're Microsoft has $21.73 billion of either revenue or profit in 2014. I didn't make a note of that. Crocs, you guys remember Crocs? The shoes that were very popular then, not so much. 550 million, right? I mean, that happens sometimes. So which of these? If you have $50 million increase here, are you happy?
Yeah.
Yeah, that's like 10%. That's outstanding. 50 million here? That's not keeping up with inflation.
Yeah.
So really, it kind of depends. Your answer is, it depends. And so what we need to talk about just briefly is what a relative or percentage rate of change is. So when we say it depends, that means it's relative to something. It's relative to where you started. So here is a relative rate of change. Relative rate of change is whatever your rate of change is. Everyone agree derivative is rate of change? Yeah. Relative to what? Whatever the original was. What's the original for f prime? F of x. There you go. So this makes complete sense. It's how much you changed over where you started. If I wanted to have a percent on this, if I wanted to have a percentage rate of change, what would I do?
Multiply that by 100.
Multiply by 100. So you guys know how to, I mean, this part is kind of the easy part. So relative rate of change is just your derivative over your function. Okay. So let's get back to this question. So let's hang on to that for just a sec. And now here's another question. I'm going to write some of this out. So let's see. Suppose you have, so we're looking at baseball caps. And so let's say that the current price is $8. Is that a normal price for a baseball hat? I don't even know.
They like their
Sure.
Well, okay. So maybe this is a cheap one at Walmart. So $8, and at that point the demand is 6,000.
Sounds about right for a cheap animal.
All right. So here's the thing. This is what we know. If we increase the price by $1, what do you expect the demand to do? Go up or go down? Yeah, usually the higher the price, the fewer people buy it. So in this case, the demand will decrease by 500. So here are a couple of questions. If your objective is to increase revenue, and so this is demand and price. If your objective is to increase revenue, do you decrease the price? And the answer is again going to be, it depends. So I'm going to give you two scenarios. Let's divide the class here. So from Ashley over, do one, and you guys do the other one. So here are two scenarios. All right, so in scenario number one, current price is $12. I'm trying to make space. $12, and the demand is 4,000. That doesn't make any sense.
Why not?
Hang on a minute. Let me see what I did. Yeah, when I copied and pasted in this, that's not what I meant. So let me try again. So current price, scenario number one, current price.
Wouldn't that be like the exact same thing?
Hang on a minute. So current price, I just copied, I didn't copy well, is $8 with a demand of 6,000. And you want to know what happens when you go to $9. So you're going to figure out what the demand is, and then for each of these, figure out the revenue. So if we know the price here, what's the demand? And then find the revenue for both. So that's this side. The other side is going to have, you guys are going to have scenario number two. So here the price starts at $12. And the demand is 4,000. Now you're going to do the same thing. You're going to increase the revenue. You're going to increase the price by $1. Figure out what its new demand is, and then figure out the revenue. Does everyone see what I'm doing? What is revenue? Compare it with price and demand. How does revenue? What is revenue? Revenue is price times. That's profit. Revenue is the price times,
Quantity?
yeah, however many you sold. Right, so price times the demand. Okay, so you've got price at $8, demand of 6,000, you can find the revenue. If it goes up by $1, the demand goes down, find the new revenue. You guys do the same, but you start with 12 and 4,000, and then if your price goes up, what's your new demand and what's your new revenue? And then let's compare answers.
Just algebraically?
Yeah, this is just number crunching. This is not hard. There's no calculus in this. This is just, it went up by 1, so this goes down by 500. And then multiply across to get revenue. It's the same thing here. This went up by 1, so this went down by 500. Multiply across and get the revenue. Okay, this is not fancy math. Well, here's,
Variables were like that easy.
yeah, and they aren't. That's why we often do some regression, because the variables aren't so easy. They aren't so simple.
Right, because like if I'm a shopper at Walmart and I see like an $8 hat, a $12 hat, I'm probably looking at the $8 hat like, that's gonna break it.
Well, that's a whole other scenario.
You know what I mean?
That's
Like,
a whole
I'm
other
gonna get
thing.
the $12
Yeah,
hat,
yeah.
like the demand's gonna
Yeah.
go up.
All right. So what is the revenue from this? 8 times 6,000. What'd you guys get?
48,000.
48,000. And if you increase the price by $1, what do we get? 49.5. 49.5. So did your revenue go up by increasing your price?
Yes.
Yes. So in this case, if you start at $8, you make money if you raise the price. What about here? Scenario number 2. 12 times 4,000 is
Same thing.
48,000.